today's group project is going to be on a vacuum forming project. So some things that you're going to need for this experiment are a paint can, a pot, some rubbing alcohol, and some dry ice. So the first thing that we're going to do is go ahead and pour our isopropyl rubbing alcohol into our container of choice, which we're using a pot. So we're going to go ahead and fill that up. And then we're going to go ahead and crush some dry ice with a mallet. And then I'm going to go ahead and put the dry ice in the rubbing alcohol. And then we're going to go ahead and put the paint can inside of a small pan on the stove and crush some more dry ice because we actually didn't have enough whenever we crushed the first time. At this point in the experiment, we wanted to go ahead and see if the water was boiling, and it actually wasn't. So we decided to crush up the ice inside of the pot, and of course scissors weren't the best option, so we went back to the mallet. We saw that the water wasn't really boiling inside of the paint can, so we decided to go ahead and take the pan out of the equation and go ahead and just stick the paint can directly on the heat. Once we put the paint can right on the stove, we saw that it was instantly boiling. Once we saw that it was boiling, we took it off the heat and we went ahead and put the top on the paint can. Once we made sure that the paint can was completely sealed off in the top, we put the paint can inside of the dry ice and alcohol mixture. We waited for a few seconds before the paint can actually contracted. We wanted to give the can just a little bit more time to fully contract, so we waited a little bit longer. The paint can looked about as contracted as it was ever going to get, so we decided to go ahead and take it out of the dry ice and alcohol mixture and show you guys what the paint can looked like in its final state. When we had opened the top of the paint can, we saw that there was actually ice formed where the boiling water was. Now we're going to show you some real-world applications. This is a video of vacuum forming, which is a simplified version of thermoforming, where a sheet of plastic is heated to a forming temperature, stretched onto a single surface mold, and forced against the mold by a vacuum. This process can be used to form plastic into permanent objects such as turnpike signs and protective covers. Thankfully, I was able to get into an engineering firm and actually try out vacuum forming for myself. Of course, I wasn't as great as the pros, and I lowered it a little bit too fast. Now we're going to go on to the energy and entropy balances.
The energy balance of crushing the paint can will look as follows. First, we'll have a diagram explaining or showing exactly what goes on. So in the original state, the uncrushed paint can has its own pressure, temperature, volume, mass, and so forth. During the experiment, it will lose heat, denoted as Q out, and work will be done on it, Wn. After the experiment is finished, the paint can will be crushed, and it will have its own different pressure, temperature, and so forth, due to the reaction. The full energy balance can be written. The original one is Qn plus work in plus En minus Q out plus work out plus E out equals delta U. In this experiment, there is no Qn in the initial state, as the paint can goes into the ice, so we will not deal with heat in. Work in will be done as the paint can getting crushed has to do with the work. However, there will be no E in or E out, as there is no mass transfer at all in this process. And there will be no work out done by this either. So it can be simplified to work in minus heat out equals delta U, which can also be written as the integral of pressure with respect to volume minus the net heat out equals mass times CV times the quantity of T2 minus T1, which is the change in temperature. This is what goes on through the experiment.
Okay, so now we're going to talk about the entropy analysis of the can being crushed, and we're going to start with our basic entropy analysis equation and a diagram of the two states and our definition of the variables at the states and the boundaries. So as we talked about before, we have no mass entering or leaving the system. So in terms of the equation, we can go ahead and cross those out. And as we've seen, the heat is leaving the can into the pan. So we can go ahead and disregard the heat in over the boundary temperature. And then with a little algebra, we can define our entropy generated as the change in entropy plus the heat out over the boundary temperature. And then if we want to look at it in terms of variables that we can measure in the experiment as more useful, we look at our definitions of the change in entropy, and from either the Gibbs or the Helmholtz equation, you can derive the change in entropy as the specific heat times natural log T2 over T1 minus the gas constant times the natural log of the pressure 2 over pressure 1. And the difference is coming from where you derive it and the definitions of internal energy, and then versus Gibbs, where you're looking at the definition of enthalpy in your derivation. So we go ahead and use Gibbs when we plug this into our own, and that gives us our final entropy generated as the specific heat at constant pressure times the natural log of the second temperature over the first temperature minus the gas constant times the natural log of the second pressure over the first pressure plus the heat out over the boundary temperature, which can be a little more useful to probably measure than the specific volumes of a crushed can.